Hi, my name is Annabella Paradise, and today I'm going to be showing you how to use mass spec, IR, proton NMR, and carbon NMR graphs in order to determine the structure of a molecular formula. Okay, so the first thing that we're going to do is calculate the degree of unsaturation. First off, our molecule is C10H10ClNO3. And the equation for degrees of unsaturation is 2C plus 2 plus N minus H minus X over 2. C standing for carbon, N for nitrogen, H for hydrogen, X for all halogens. And so, plugging in the right numbers, we get 2 times 10 plus 2 plus 1 minus 10 minus 1 all over 2, and then that equals 6. And so this tells us that the structure of our molecule is going to be a benzene ring, and it's most likely going to have a few double bonds in it just to give it that higher degree of unsaturation. We're also going to calculate the mass of our molecule, and calculating that, the mass is equal to about 227 grams. And on our mass spec, it doesn't go up to 227, but it's around here. And so we're going to denote that M plus 227 over here, and then we're going to start calculating the fragments based on these peaks. Our highest peak is considered the base peak, and our base peak happens relatively late in the mass spectrometry, so we are only going to calculate these fragments here, which equal 3.5, because this one is at about 123.5. This one's going to be 3 because it's at 124. This one's going to be 2.5 because it's at 124.5. And this one's at 125, so it's going to be 2. These fragment numbers typically tell us the most common fragments, and none of these numbers are actually most common fragments, so mass spec doesn't really tell us a whole lot. So next we're going to move on to IR, and I've outlined all of the regions for IR. So the regions go 1 through 5, and these X's are just regions that typically there's not any signal. And then this is the fingerprint region, which we're not going to focus on in this video. So this first region right here, this peak that occurs at about 3,300 nanometers, is actually in the region of the NH stretch, and the shape of it is very pointed, so it tells us that this could be an NH stretch here. And then the second region that we have here in zone 2, we have this relatively large and quite wide and bulky peak, but it's on the lower side of the region, so it's before 3,000, between about 3,000 and 2,800. And so this region is the sp3, and it kind of just tells us that we're going to have sp3 carbons within our molecule structure. Going on, zone 3 doesn't have any signal, so we're not going to worry about that one. Then zone 4 shows this peak right here. Zone 4 typically shows carbonyls, which is C double bond to O. And so this region tells us that it's probably a carbonyl, and because it's on the lower side, it could be a carbonyl for an amide. But it looks like there's 2 peaks, so 2 separate peaks, so there could be more than one. So we'll just keep that in mind and know that this region is showing C double bond to O. And then our final region, it has 2 peaks on this lower half, and that typically shows an aromatic benzene, which is consistent with our degree of unsaturation. And then there's also a few more peaks, and these regions are typically amines, so we can just keep that in mind, that this C double bond to O could also be part of the amide, and those signals can connect to this NH stretch that we found over here. So this could also show the presence of an amide. So the next graph that we're going to look at is the proton NMR graph, and that graph looks at the hydrogens attached to the atoms within the structure. And this is how we're going to tell the formation of our molecule in the way that the structure is. We're going to do this using the integration numbers of the hydrogen, and we're also going to use the n+1 rule, as well as the information that we found out from our last 2 graphs. So doing this, we're going to start with the aromatic benzene because it is the most obvious place to start, and we had 2 graphs telling us that that's what we were going to have, which was the mass spec, or actually we found that out using the DOA, and also the IR graph told us that we were going to have an aromatic. And this 2,2 multiplet right here is where the aromatic hydrogens are, and this tells us that the substituent groups on the aromatic are going to be para and leaving 2 hydrogens on either side, and substituent groups will be here and here. Going over here to this alkyl region, we know that there's going to be a carbon, and because of integration it's going to have 3 hydrogens, so it's going to be a terminal alkane with 3 hydrogen. And its integration is 3. So we know that what's next to it has to have 2 hydrogens because the n+1 rule states 2 + 1 = 3. Because there are 3 peaks here, there are 2 small peaks on either side plus this larger peak. So that tells us there's most likely going to be a carbon here with 2 H's on it, which accounts for this peak right here. This peak has, the n+1 for this peak is 4 because of there's 4 peaks here, 2 on either side, and then there's 2 in here. It's a little hard to see, which accounts for the 3 hydrogen here, plus 1 = 4. That also tells us that what's on this side is not going to be attached to hydrogen. So we know that we have carbonyl groups, so we're going to go back over here. We also know that we have an NH stretch to account for, and that this is what our NH stretch is going to look like, and it's only going to have 1 H because of the integration of 1, and this little peak right here, the shape of it shows that that's going to be the NH stretch. And because of how far downfield it is, we know that it's going to be bonded to something that's attached to an oxygen or an oxygen itself. Due to our IR, there's going to be about 2 carbonyl groups. So we're going to have 2 more C's, and that will account for all of our carbons. And then since we said before that we know that this is not attached to anything that has a hydrogen on it, we'll add an oxygen here, and we'll double bond these carbons to oxygen as well to account for our 3 oxygen within our molecular formula. Finally, we have a chlorine to account for, and we only have 1 other side to attach a substituent group. So we're going to attach that substituent group right over here, and it's just going to be chlorine by itself. Next, we're going to go through and just make sure that the integration and the n+1 rule work for this structure, as well as it accounts for all of the molecules within our molecular formula. So starting on this side, we have a carbon bonded to 3 hydrogen, which accounts for the integration on this peak right here, which is 3. And this peak also has 3 peaks, which accounts for the n+1 rule. So the carbon next to it has 2 hydrogens, and 2 + 1 is 3, which accounts for the 3 peaks. So these hydrogens right here go to that peak. Next, this carbon right here has 2 hydrogens on it, which accounts for the integration right here. And it has 4 peaks. Again, these 2 are a little hard to see, and then there's 2 small ones down here. And so that accounts for the n+1 rule here with the carbon, 1, 2, 3 hydrogen. And so 3 plus 1 is 4 peaks. And so this group right here of hydrogens goes to that peak. Next up, we have this nitrogen here that has a hydrogen on it, and it only has 1, which accounts for this peak, as well as the fact that this is a peak that symbolizes the NH stretch. And so it's only 1 peak. There's no other carbons that have hydrogens attached to it. So we know that this goes to this peak right here. Finally, we have our aromatic hydrogens that go to this 2,2 multiplet integration right here. And so we can just label this region right here as aromatic hydrogens. And those are shown here, just to give a visual of what it looks like. The next thing that we need to do when we're going to determine whether or not this is the proper structure is we have to count just to make sure that we have the correct number of each element within our structure. So we have 10 carbons on this aromatic benzene. There's 6, 7, 8, 9, 10 carbons. We also have 10 hydrogens, and so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 1 chlorine, which is accounted for right here, 1 nitrogen, which is accounted for right here, and 3 oxygen, which they're right here, 1, 2, and 3 right here. We can also see that our molecule is not symmetrical, and the only thing about this molecule that's really symmetrical is the benzene and the fact that we have 2 substituent groups, but other than that, the substituent groups are not equal to each other, which leaves our molecule being asymmetrical. The final graph that we're going to look at is carbon NMR. So we're just going to account for the placement of the carbons and as well as de-shielding to kind of show that the structure that we drew is correct. It's just kind of a confirmation. So what we're going to do is we're going to label these peaks descending, and since we have 8 peaks here, we're going to label it from 8. So 8, 7, 6, 5, 4, 3, 2, and 1. So first off, again, we have this alkyl region here, and this first one, it's the farthest carbon away from oxygen, so it's de-shielded the least, so that carbon can be assigned to that peak. This carbon is directly bonded to an oxygen. Even though it is an alkyl, it's going to be de-shielded, which is why it's not in the typical alkyl region, but can still be accounted for this one. This one is 8, and this one is 7. Next we have these 2 carbon right here, which are probably the easiest to assign. So this carbon right here, it's double bonded to an oxygen, which pushes it downfield a lot, and so that leaves us with these 2 peaks right here. And so it's also bonded to an oxygen because it is an ester, so it's going to be downfield the most and de-shielded the most by these oxygen. So this carbon is going to be assigned the integration number of 1. Next we have this carbon, and it's only double bonded to an oxygen, so it'll still get pushed downfield because of de-shielding, but not as much as this one because this one's bonded to 2 oxygen and this one's only bonded to 1. So this one's an assignment of 2. So finally we have our aromatic carbons, right here, and there's 6 of them. We only have 4 left to assign because these carbons opposite of here tend to flip around, so they're not as assigned as accurately, and they can kind of be flip-flopped within the spectrum. So this one right here, since it is bonded to a chlorine, it's going to get the integration of 4, which is right here, and this one's going to get the integration of 3 because it's a little bit closer to these oxygen over here. And then finally, these ones are going to have 5 and 6 respectively. So these two are going to have 5, these two are going to have 6, and they're just kind of, it's really kind of unknown which ones are which in here. So which is why they both get the assignment of 5 and 6. But our deshielding matches with the structure. So it tells us that this structure that we drew up here is the correct structure for our molecular formula, and it matches all of our graphs. So thank you for watching.